We report work that we did in the early stages of the COVID-19 pandemic as part of an initiative that brought together modelers and visualization experts at a time where there was a scramble to understand its implications. My co-authors were developing a COVID-19 model, and our challenge was to rapidly co-design interactive visualization means to explore the high-resolution model inputs and outputs at multiple scales. Our solution was to use what we call gridded glyphmaps and design glyphs to facilitate a set of agreed model development analytical tasks. We present our designs and show how they were used and how they can be generalized for other spatial modeling work. The Scottish COVID-19 Response Consortium was an initiative that brought together modelling and visualisation experts to help understand the implications of the COVID-19 pandemic. We were one of the specialist modelling groups within the consortium. My expertise are in information visualisation, and my co-authors had developed a model called Ecosystem JL, simulating the dynamics of plant growth, competition and reproduction. They repurposed it for modelling the spread of COVID-19. The model takes 1 km square resolution age stratified population data and a set of initial infection seed locations, and it simulates the spread of COVID-19 over a 30-day period. In the model outputs, the resident population is classified into different COVID infection states. This is how the model transitions between the COVID infection states. Populations start off being susceptible, and then individuals become exposed. Exposed individuals can become asymptomatic, who then go on to recover, or pre-symptomatic, who then go on to be symptomatic, who then either recover, are hospitalized, or die. The likelihood of moving between these states depends on the individual's age, which is why we have the population input data. We also have pollution levels as an input, where this likelihood is modified due to pollution's effects on the respiratory system. Help for investigating the balance of these inputs was one of the reasons for this collaborative work. The main challenge for facilitating interactive visualization means for model development was the multivariate and high-resolution nature of the data. Model developers usually produce multiple univariate graphics that summarize model outputs at high levels of spatial aggregation. This makes it very difficult to explore the outputs and to identify and check spatially local detail. It is also difficult to consider how multiple variables may vary together over space. Our requirement was to co-design interactive visualization means of exploring multivariate model inputs and outputs at multiple spatial scales. Our solution to summarizing multiple variables of data together over space was to use gridded glyphmaps. These grid space summarize the multivariate data that lie within each grid cell as glyphs or mini charts, and then embed these in the cells. This enables, for example, spatial variation in the amounts of population in all COVID infection states to be summarized. Our solution to exploring at different scales was to add interaction, with zooming that regrids the gridded glyphmaps to different scales on the fly. We also added interactions that switched between glyph designs and provided details on demand. This is a gridded glyphmap of population. Glyphs are inverted population pyramids, which indicate population size by age, with younger ages at the top. Zooming in increases the resolution, and it can be observed that the population in central Glasgow is younger than average. This is in common with most urban areas. Here we switched the glyph design to show the output of a model run, and here we've switched the glyph to show normalized proportions. Each age group is divided into the COVID-19 infection states previously shown. The time steps are animated, but moving the mouse on the timeline above enables time to be interactively scrolled back and forth. We came up with some analytical tasks to support the modelling process. The first one is to look at the spatial distribution of the multivariate model inputs and outputs. The second one was to look at the parameter values and how they affect the model outputs. The final one was to look at how different model outputs compare. This could be used in scenario planning where different lockdown policies could be implemented. We ended up with 4 basic glyph designs in absolute and relative versions. You have seen these two already. The relative version of the inverted population pyramids, inverted for no good reason, on the right, shows a population age structure even for small populations. The infection time series glyph aggregates the age but shows the infection progress in a static graphic. The comparison glyph below shows the difference between the two models. Above the horizontal line is where the infection category is greater than the baseline, and that below the horizontal centre is where the infection category is less. In this case, the baseline is the less severe of the two models. These glyphs indicate that the peak difference is around 3/4 of the way through, and there's not much difference at start nor end of the model time period. As mentioned, there are absolute and relative versions of the glyphs. Relative versions remove the effect of population size, but proportions can become unreliable when populations are low. We experimented using proportional symbols in the middle to draw attention to proportions that might be unreliable with the smaller symbol size. However, we preferred using opacity on the right as it reduces the salience of proportions that may be unreliable and unimportant. Flicking between two model outputs is one approach to comparison. However, we found the directly encoded differences between the models in the glyphs to be more effective. Looking at these spatially indicated that in Edinburgh there are 2 difference peaks between the models, compared to other places. This demonstrates the importance of considering spatial variation. We found gridded Glyphmaps and our designs and interactions to be useful tools for developing spatial models. They are likely to work in other contexts, perhaps even also in non-geographical spaces. The original prototypes were implemented in Java and are specific to our COVID-19 model. However, we have been working to generalize the concepts and have re-implemented much of this in JavaScript via observable notebooks. We hope that this paper and this notebook will inspire you to experiment with gridded Glyphmaps in your applications. We are also working on JavaScript libraries to make this easier. We have demonstrated gridded Glyphmaps to help support spatial modeling and presented glyph designs and interactions that we found useful. We think that these are generalizable to other spatial contexts, and even perhaps to non-geographical spaces, where multivariate data needs to be explored spatially, and these data need to be considered at multiple spatial scales. We suggest plenty of directions for further research, and we encourage experimentation with our examples and observable implementation.